And this brings us back to where we started with a managed system to control laboratory risk. All of those numbers are too complex, too time-consuming to manipulate yourself. But now we have an app, we have a solution, we have something that can optimize everybody's quality control. At the least, the ability of the QC procedures to detect medically allowable error should be evaluated. If these processes create too many bad results, will these processes alert staff before too many patients are exposed to risk and some of them are seriously harmed? The question we're trying to ask is, will your QC processes maintain an acceptable risk level? This is one study. This is the study we've been talking about. We examined QC data for glucose, INR, protimes, hemoglobin, and sodium from 48 instruments in 3 labs to answer the question, is risk level acceptable? In 20 runs, these 48 instruments, and we approximated the numbers, would have produced 636,000 patient results. The existing QC processes take an average of 10 runs to alert staff to a simulated medically significant error. So we defined a medically allowable error, we simulated a shift that would cause the method to produce 5% bad results, and then we said, how many runs will it take to detect that error? With the existing QC, almost 500,000 patients would be exposed to risk if every method failed, and 25,000 would receive medically invalid results. By just optimizing your quality control processes, you can change the average runs to reject from 10 to 2. Now that's still not acceptable, and the program will advise you and take you through how to improve that. But simply by optimizing those QC processes, you can reduce the number of patients who would be exposed to risk, and again, this is if every method failed, down to 72,000. That means only 3,500 getting medically invalid results. Now those are still big numbers, folks. That's if every method failed. Obviously, every method will not fail, but this is the total risk that you are exposed to. This is the risk you're protecting yourself from. You're running quality control to protect these 600,000 patients. Right now, you're still exposing 71,000 to risk. With that information, now we can create reports that are meaningful for everybody who cares about quality. Everybody, every single person, from the patient to the lab director to the administrator to the frontline staff, can say, okay, what is the reference for the medical goals for this test, and show me your report card. So you have to know you're meeting a reference standard, you've set a reference standard, and are you meeting it? Just at a glance, anybody can assess patient risk. Is the risk acceptable, unacceptable? Does method quality need improvement, or is there an opportunity to improve your quality control process? This could be individual regions, this could be individual instruments, this could be individual laboratories, departments. You can slice and dice that report card any way you want. For the high-level people who don't care about all the details of the specifics, they get a summary report. When you add up the details, you can look at the number of individual patients exposed to risk with existing processes, the number of patients exposed to risk with optimized processes, and the potential reduction in patient risk and cost. For these people, all they need to say is, hey, you can do better. You can reduce patient risk, and you can reduce the number of medically invalid results. When you come down a notch to the lab directors, who then carry this on to talk to the QA managers and the working managers, they have the risk-based quality grade that gives them a lot more information to look at. This report is also highlighted to draw your attention to data that is exceptionally high or low. But you don't need to go through all those numbers. Let the computer sort that out for you. So you know the ones that are highlighted are ones that you need to look at. These are going to take 11, 13, 14 runs to detect clinically significant error, when you could do it in one run, except for this fellow who's taking 4 runs to do it. Just by looking at this chart, you can immediately focus in on methods that require your attention. And again, here's the incentive. This is the potential. If you can optimize those methods, here's what it means to patient care. You can break it down within the lab then by test. The analytes we examine, now isn't this an interesting pattern? The INRs and the sodiums are all grade D, except for one INR which currently is failing. These ones, we need to improve the analytical process. Did you know that before? The RBQ report card is a tool that these busy people can use to focus on exactly what needs their attention. For these busy people at the front line, you get simple, clear messages. We validate the analytical process. Yes, it passes. It meets your medical goals at this time. We validate the effectiveness of the QC process. In this case, it fails. It requires action. And we validate the efficiency of your QC process. It passes. There are no unnecessary QC flags. So now we've arrived at the Quality Optimizer report. Quality Optimizer gives you 3 pages of detail that you need at the lab level. You start with the summary report. The first thing you see is that this is a risk-based quality grade C. The method is okay now, but QC will not detect clinical failure due to poor QC design. All we have to do here is improve the QC process and we can reduce patient risk. It gives you an evaluation of the analytical process quality at this time. So now you can see from the performance bars that the green, where you are now, is well separated from the red, where you would be if the method failed. That's all QC is about. It's separating the good from the bad, telling you when the good turns bad. It's easy to separate those two populations. These methods have a margin for error of over 6. Margin for error is the number of standard deviations the method can shift before it reaches unacceptable risk levels. It tells you how well the method is doing now, but margin for error, like sigma, does not give you an indication if the QC process will prevent patients from risk if the method fails. Quality Optimizer performs that assessment, and it tells you clearly, does the QC prevent risk? Yes or no. In this case, no. It assesses if you're minimizing false positives, and in this case, you are. This report tells you you have an opportunity to reduce patient risk and reduce costs. Quality Optimizer creates a full individualized QC process as recommended by IQCP and EP23. It gives you the QC rule, it gives you the sample frequency, it advises if you need to increase frontline chart review, supervisor chart review, and any action you need to take. It does what we've just done very slowly and in detail with those simulators. It generates 50 points based on your current mean and SD on current method performance. Then it simulates a clinically significant error, an error that would make 5% of your patients reported receive medically invalid results. You can see here that there's only one run flagged. Just by optimizing your QC process, just by putting the real mean, the real SD on the QC chart, and selecting the right rule, you can detect this change in one run instead of possibly going on for 20 runs. The same thing happens for every single control. So Quality Optimizer recommends and verifies an optimized QC process, and it verifies your existing QC process. Quality Optimizer creates new metrics to let you understand patient risk. The third page of the Quality Optimizer report, the bottom line report, brings down the details to show you that in this case, this analyte has a margin for error of 7.1. It's doing very well now. This method can shift 7 SDs before it's in trouble. The lab is using a 1-3S rule. Of course they'd detect it, wouldn't they? That's the problem. The lab is not really using a 1-3S rule. Because they've multiplied their standard deviation and modified the mean, what they think is a 1-3S rule is actually a 1-10S rule. That means that they would not flag a clinically significant error until a QC point was 10 standard deviations from the mean. So when we simulated a failure that would cause 5% of results to be medically invalid, it took 11 runs to detect that change, and they would have reported 344 medically invalid results. Just by changing the QC rule and putting your real mean and SD on the QC chart, you can reduce that risk to 31 medically invalid results and reduce the potential cost from $13,000 down to $1,000. That cost, again, is calculated at $20 per medically invalid result and $1 for each patient at risk. The bottom line does just that. It adds it up to the bottom line. With this method, you can prevent risk to this many patients, you can prevent medically invalid results to this many, and you can save this much money. Quality Optimizer quantifies patient risk. It puts a dollar value and a number and a patient face on the cost of failure to control quality. In this instance, we looked at 48 methods. We said how many patients would be exposed to risk in the next 20 runs if every single method failed today. There was a significant reduction in the number of patients exposed to risk by using OptimiZe QC processes that detect medically significant error sooner. We discovered that in this instance you could avoid risk to almost 425,000 patients, and if 5% of those receive bad results, you could avoid sending out over 20,000 medically invalid results. Now remember, this is if every method failed. The maximum potential clinical savings, so the risk you're exposed to now that you would not be exposed to by optimizing your QC processes, is a total of almost $1 million. To do that, it's actually going to cost you a little bit more in the lab until you get your QC under control and improve the processes that need improving. If every method fails right now, you would be exposed to a significant amount of financial risk. Every method is not going to fail. It's sort of like fire insurance, though. You don't know which one is going to fail. So your maximum net savings, even if only one method fails, is $31,000. And if it's one, which one will it be? Your existing QC process effectiveness, the effectiveness of it to prevent risk is 22%. Your optimized QC process effectiveness is 89%. We have, right now, in December 2014, a once-in-a-lifetime chance to get it right the first time. Now we have a process to quantify and improve the effectiveness of existing and proposed QC processes to protect patients from medically invalid results. I think the question is not as much why would we do this as why not, and that leads to how. What we're trying to do, what Awesome Numbers, Zoe Brooks is trying to do, is to replace the methods we're using today for quality control with risk management. Right now, we have recommended TEA limits based on state-of-the-art or statistical limits defined by lab scientists. The local TEA limits, if they're defined, are set by the medical director based on personal opinion. The hospital on one side can use different medical goals than the hospital on the other side of the street, simply based on the opinion of the medical director. QC processes are inconsistent, unverified, and typically ineffective to alert staff to clinical failure. Staff understanding of and response to signals from QC charts is inconsistent and unverified. When people take their training, they don't get a chance to practice quality control. They don't get a chance to see what does it really look like if it fails. There's a big weakness in the educational program. And currently, if methods fail, over 50% of patients will be exposed to the risk of medically invalid results. We can do better. Instead of using statistical limits, we can have recommended medical goals and acceptable risk levels defined for general clinical settings by medical practitioners, by the people who make the decisions in those settings. We can replace that local medical opinion of only the lab director with goals and risk levels that are managed by the medical director and approved by the local medical practitioners, that the local medical doctors say, this is the level of quality we need, this is the level of quality we'd like you to manage. We can replace those inconsistent QC processes with automated QC process design that is verified to alert staff as soon as possible to unacceptable risk levels. This is where Quality OptimiZe comes in. If we put Quality OptimiZe as an app into every lab, we can eliminate 90% of the problem that's going on with QC right now. We can work with universities to create verified educational and competency assurance programs to confirm staff action to mitigate risk. We can put them through drills, we can let them practice, we can do proficiency testing for the quality control component. You're investing all of this in quality control. Let's make sure it works. And if methods fail, if your staff are certified competent, you can maintain a process where less than an acceptable number of patients will be exposed to the risk of medically invalid results. We can convert quality control to risk management. I want to thank you for listening to this. I hope you've understood the problems that we're facing now with quality control, the opportunity that we have to improve, and the truly rare opportunity we have to bring people together to get this right the first time. When we transition from the mess we have now with statistical process control to risk-based management, we can give it a process, we can give it direction, we can give it guidance, and we do have an opportunity to get this process right the first time.